Imagine you are Nick Fury. You need to form multiple Avengers teams, but you don't know every hero by name, and you have no labels, but just the data, how they fight, what powers they use, and how they behave. You notice a few heroes always surrounded by gadgets and technology: Iron Man, Shuri, Rocket. Clearly, they're techies. Then you spot the powerhouses: Hulk, Thor, Captain Marvel. They crush enemies with brute strength and overwhelming force. And also, there are the mysterious ones: Doctor Strange, Scarlet Witch, Loki, bending time, space, and minds. Without knowing their names or roles beforehand, you've grouped them by patterns in their abilities. That's exactly what clustering does. Clustering is like building Avengers squads without a roster, just based on who's similar to whom. No labels, just natural groupings from the data itself. Clustering is an unsupervised learning technique in machine learning. In this video, we'll break it all down, step by step, as we explore what clustering really is and how it works in machine learning, dive into real-world use cases that show just how powerful it can be, understand the role of distances in clustering and how we measure similarity, and then go deep into the types of clustering techniques, including K-means, K-medoids, agglomerative and divisive clustering, DBSCAN, optics, sting, and Gaussian mixture models. We'll also cover how to visualize clustering results using dendrograms and silhouette plots, and finish with an introduction to TSNE, a powerful tool for visualizing high-dimensional clusters. By the end of this video, you'll not only understand clustering, you'll be ready to build your own squads of data, no shield clearance required. Let's get started. Clustering is an unsupervised learning technique, which means the model doesn't need any labeled data to learn. Instead, it figures things out on its own by grouping similar data points together based on their characteristics. The purpose of clustering is to identify natural patterns or groupings in a data set, without being told what those groups should look like. Think of it like this. Imagine a cricket batter's wagon wheel. Each colored line on the field shows where a shot was played. Some go straight down the ground, some to the offside, and others to the leg side. Over time, these shots can be grouped based on direction, distance, or frequency. The result, natural clusters emerge, like all cover drives forming one group, all leg glances another, and lofted straight drives yet another. These aren't manually labeled, they're just grouped based on similar behavior. That's exactly what clustering does with data. The key concept is, items in the same cluster are more similar to each other than they are to items in other clusters, just like similar types of shots appearing in the same zone on the wagon wheel. So whether it's cricket shots or customer data, clustering helps us make sense of complex patterns in a smart and intuitive way. In the real world, most data doesn't come with neat little labels. You won't always know in advance what kind of customer you're dealing with or what pattern you're looking for. That's where unsupervised learning steps in. Instead of relying on predefined tags, the machine learning model explores the data on its own, finding similarities and forming natural groups, or clusters, based on common features. Let's break that down using a simple analogy. Imagine the characters from The Simpsons. They all look different, dress differently, and have their own quirks. But if you look closely, you can still form meaningful groups, like all the kids, all the adults, or even characters with blue hair. That's clustering at work, no labels, just patterns. Another relatable example. Think of a hotel app targeting potential consumers. It doesn't know each person's favorite dish or how often they dine out, but by analyzing their age, food preference, visit frequency, and spending habits, the app can group users into clusters like frequent young diners or occasional family guests. This allows for smarter, personalized marketing, again, all done without any prior labeling. Now let's look at where clustering is used. It powers document classification, customer segmentation, fraud detection, healthcare diagnostics, and even recommender systems. In banks, it helps spot unusual patterns in transactions. In hospitals, it can group images based on disease stages. It's like giving machines the ability to observe and organize just like humans, but faster and at scale. Now let's see how clustering looks in action. In a real-world retail scenario, imagine a restaurant chain like this one, trying to understand its customers better. Each outlet has a diverse set of visitors, and the app here helps group them based on specific characteristics, using clustering. For example, one set of clusters could be based on food preferences. Some customers are strictly vegetarian, some eat both veg and non-veg. and others may even be grouped by alcohol preference. Then we look at marital status, whether the customer is a single male, single female, a couple, or a family with kids. This helps the business plan seating arrangements, promotions, and even menu options accordingly. Another set of clusters is based on how often they visit. Someone who dines once a month is very different from someone who comes in every day. Each group has different value and loyalty potential. Lastly, customers can also be grouped by their preferred dishes. So, if a majority of people in one cluster love dish 3 and dish 5, the restaurant might promote combos or offers featuring those dishes. What's key here is that all these clusters are created without any labels. The data is raw, and the algorithm is doing the heavy lifting to find patterns. That's the beauty of clustering. It lets businesses personalize at scale, making better decisions without needing predefined answers. Clustering isn't just about grouping, it also depends on how we measure distance between points. Let's look at some common distance metrics. First is Euclidean distance, the most familiar one. Think of a crow flying directly from point A to point B. It's a straight-line path, just like using a ruler on a map. Then there's Manhattan distance, which is more like walking city blocks. You can't go diagonally. You have to follow the grid lines. It adds up all the horizontal and vertical movements. Minkowski distance is a more flexible formula. When PPR1, it becomes Manhattan distance. When PPR2, it behaves like Euclidean. It gives us the ability to generalize based on our needs. Now, Gaussian similarity doesn't look at distance directly. Instead, it compares the angle between two vectors. Imagine two people standing in the center of a circle and pointing in different directions. In the chart here, you can see that woman and queen point almost the same way, so they're more similar, while man and queen are farther apart in angle. Lastly, Jaccard's similarity focuses on how much two sets overlap. The Venn diagram here shows that the more common elements two groups share, the closer they are. The fewer commonalities, the more dissimilar they become. All these distances help us decide how to cluster our data, and choosing the right one can dramatically change our model's performance. Now, let's look at the main types of clustering algorithms. These are broadly grouped into 5 categories. First, partitioning clustering, which includes methods like K-means and K-medoids. These divide data into distinct non-overlapping subsets based on similarity. Next, we have hierarchical clustering, which builds nested clusters in either a bottom-up approach, called agglomerative, or a top-down approach, called divisive density-based clustering methods, such as DBSCAN and optics, identify clusters as dense regions in the data, which makes them particularly good at handling noise and clusters of arbitrary shapes. Grid-based clustering like Sting and Click divides the data space into a grid structure and performs clustering on the cells rather than individual data points. Finally, model-based clustering uses probabilistic models. Examples include Gaussian mixture models and the expectation maximization algorithm, which estimate the probability that each point belongs to a cluster. Choosing the right algorithm depends on your dataset's size, shape, and noise tolerance. K-means clustering is an unsupervised learning algorithm used to group unlabeled data into clusters. The number of clusters, represented by K, is predefined before the algorithm runs. So if K equals 2, the data will be grouped into 2 clusters. If K equals 3, it will form 3 clusters, and so on. Let's understand this with a grocery store analogy. Imagine a store manager organizing items into different sections, say fruits, vegetables, and packaged goods. These are 3 distinct groups, so we can say K equals 3. The algorithm would then cluster similar items together, just like the store manager does when placing bananas with other fruits or canned soup with other packaged items. Each item is grouped based on similarity, and the algorithm keeps refining the groupings until the best separation between clusters is found. Let's break down how the K-means algorithm works, using our grocery store analogy with 3 sections: fruits, bottles, and packets. Initialization. First, we decide on the number of clusters, in this case K equals 3. Then, we randomly place a few products into each of the 3 sections just to get started. Assignment. Next, we look at each product in the store and assign it to the section it fits best, based on characteristics like food type or storage needs. For example, apples and oranges go in the fruits section, while juice bottles go on the shelf with bottles. Update. After everything is sorted, we check to see if the sections still make sense. Maybe the fruit section is too full, or some items seem out of place. We recalculate the center of each section, which means finding the average product type, and adjust the groupings. Convergence. This whole process is repeated until the arrangement settles and no major changes are needed. Eventually, each product is in the section where it best fits, and that's your final set of clusters. K-medoids is a clustering algorithm that functions similarly to k-means, but with a key difference. Instead of using the mean of points as cluster centers, it uses actual data points called medoids. This makes it more robust to outliers. In summary, k-means uses centroids, which are average positions, while k-medoids uses real data points. This difference allows k-medoids to handle noise and outliers more effectively. Agglomerative clustering is a hierarchical clustering method that starts with each data point in its own cluster. Gradually, the most similar clusters are merged step by step, forming a hierarchy from the bottom up. Think of it like a strategy game, such as Plague or World Conquest. At the beginning, each player controls just one territory. As the game progresses, players form alliances with neighboring territories that are similar or strategically compatible. These small alliances grow as more regions join, mimicking how clusters combine in agglomerative clustering. Divisive clustering is a top-down hierarchical method. It begins with the entire dataset grouped into a single cluster, and then splits are made step by step to form smaller clusters. Imagine you're planning a vacation. Using a top-down approach, you'd start with the big picture, things like your destination, accommodation, major activities, and itinerary. Once those key decisions are made, you'd break them down into more specific actions and details. Similarly, divisive clustering first defines the overall group, then systematically breaks it into smaller, more refined clusters. Spatial refers to how things are arranged in space, their position, distance, and relationship to one another. Imagine you're at a playground. There's a slide, some swings, a sandbox, trees, a rest area with benches, and a parking lot nearby. The slide might be close to the swings, but the sandbox could be farther away. The trees offer shade near the benches, while the parking lot is placed at the edge of the playground. You'll notice that people tend to move between the slide and swings because they're close together. That's spatial proximity. Parents often sit in the rest area under the trees because it's comfortably shaded and near where the kids play. The distance from the parking lot to the playground shows another spatial relationship. When designing the playground, things are grouped or spaced out depending on how they're used together. So overall, spatial is about where things are located, how close or far they are, and how they connect in a space, just like the layout of a well-planned playground. DBSCAN, density-based spatial clustering of applications with noise. Imagine a city with many neighborhoods. Some of these areas are tightly packed with houses, while others are more spread out or even empty. DBSCAN works like a smart urban planner. It finds and groups the crowded neighborhoods. These are called clusters. But if a house stands too far away from others, or is part of a very small group, DBSCAN marks it as noise or an outlier. This helps us separate dense, meaningful data from scattered, irrelevant points. Parameters required for DBSCAN algorithm. The DBSCAN algorithm needs two key parameters, epsilon and minimum points. Epsilon defines the neighborhood around a data point. If the distance between 2 points is less than or equal to epsilon, they are considered neighbors. If the epsilon value is too small, many points may be labeled as outliers. If it's too large, separate clusters may merge together. One way to find a good epsilon value is by using a k-distance graph. Next is minimum points, which is the minimum number of neighbors a point must have to be considered a core point. The larger the dataset, the larger this number should be. A general rule is minimum points should be greater than or equal to the number of dimensions in the data plus 1. So, if you have 2 dimensions, the minimum points value should be at least 3. OPTIC stands for ordering points to identify the clustering structure. It's an advanced clustering algorithm inspired by DBSCAN, but it improves on it by handling data with varying densities. Think of a tourist with a detailed map trying to decide which places to visit. Instead of grouping all attractions based on a fixed distance like DBSCAN, the tourist evaluates how densely packed areas of interest are. They follow a path that reveals not only the popular tourist zones, but also how these spots are spread out. In the same way, OPTICS processes points in an order that helps reveal the true structure of clusters, adjusting for different densities and uncovering patterns DBSCAN might miss. Let's look at how optics works using the analogy of a traveler navigating through a network of landmarks. First, the traveler picks a starting point. This is like selecting an unprocessed data point. Then, they calculate how accessible or close the next destinations are, similar to computing the core distance. The traveler expands their journey by checking how reachable nearby locations are from the current one, planning the route in a smart way, just like optics expands clusters by calculating reachability distances. This process continues step by step until all destinations, or data points, have been considered, building a complete and insightful map of how the clusters are structured. Sting is a grid-based clustering technique that organizes data by dividing the space into rectangular cells. Instead of clustering based on individual data points, it focuses on the statistical information within these predefined areas. Think of it like organizing a library. Instead of looking at each individual book, imagine dividing the entire library into sections based on genres: fiction, nonfiction, science, history, and so on. Each section, like a cell in Sting, holds a collection of books, and we analyze the section as a whole rather than each book separately. This allows Sting to efficiently identify clusters by analyzing how dense or sparse these sections are, just like how a librarian might assess the popularity or variety within a genre section. Gaussian mixture model, or GMM, is a probabilistic clustering technique. It assumes that the data is generated from a combination of several Gaussian distributions, each representing a different cluster. But instead of assigning each data point to one cluster, GMM calculates the probability that a point belongs to each cluster. Let's take a real estate example to understand this. Imagine you're evaluating house prices. A large modern house will likely fall into the luxury category, while an old, rundown house might belong to a budget category. But what about a large old house? It's hard to say definitively. GMM handles this uncertainty by estimating parameters like means, variances, and mixing weights to tell us, probabilistically, how much the house belongs to either cluster. This nuanced approach helps us understand overlapping categories, where things aren't black or white, but shades of probability. A dendrogram is a visual tool used to represent hierarchical relationships in data, particularly in clustering algorithms like agglomerative clustering. It shows how clusters are formed step by step. At the bottom of the dendrogram are the leaves, which represent individual data points. As we move upward, merge points indicate where clusters come together. The height of each merge reflects the distance or dissimilarity between clusters at the time of merging. In agglomerative clustering, we start with each data point as its own cluster and merge them progressively. In contrast, divisive clustering starts with all data points in one big cluster and splits them apart. The dendrogram helps us visualize and understand this entire clustering process from beginning to end. A silhouette plot is a visualization tool used to evaluate how well data points fit within their assigned clusters. It helps us understand the quality of clustering by measuring how similar a point is to its own cluster compared to others. Each point receives a silhouette coefficient, ranging from 1 to 1. A score of 1 means the point is well matched to its own cluster and very distinct from neighboring clusters. A score of 0 means the point lies right on the boundary between two clusters. It's uncertain where it truly belongs. A negative score suggests the point might be in the wrong cluster. Silhouette plots give us an immediate sense of how compact and well separated our clusters are, making them a vital tool in cluster validation. TSNE, or T-distributed stochastic neighbor embedding, is a powerful nonlinear dimensionality reduction technique designed primarily for visualizing high-dimensional data. Unlike linear methods like PCA, TSNE excels at preserving the local structure of data, meaning it keeps similar points close together in the lower dimensional output. This makes it especially useful for identifying natural clusters or patterns that may not be obvious in higher dimensions. By reducing data to 2 or 3 dimensions, TSNE helps us see how data points relate to each other in a way that's intuitive and visually meaningful, even if the original data is highly complex. And that's it. You've just assembled your own data-driven Avengers team. If this video helped you understand clustering in a whole new way, don't forget to like, share, and subscribe for more machine learning insights and breakdowns. Whether you're grouping heroes, customers, or cricket shots, clustering helps you uncover powerful patterns hiding in the data. Thanks for watching. See you in the next one.